Hopefully everyone can see that now. So I am Andrew McKenna. I work for Global Associates as an operations director. I've been in the industry about 21 years, doing various things. Started as a AC engineer, heating and vent, then moved into a company called Trend. Worked for them for about 6 years. Went from Trend to managing a team. Sorry guys, you okay to just mute? Thank you. So went from Trent, went to a company called ISS, managed a team for a few years before moving to a company called Engie, getting more into the smart buildings, before finally at my role now, which is for Global Associates as an operations director. I guess who would we aim this at? This is really aimed. I think there's a bit of a shortage of skill within the BMS industry. So really this is aimed at the BMS industry. For anyone who's new coming on from maybe, one of the main roles, electrical, mechanical, air conditioning, plumbing, any of these roles where there's a direct tie into BMS, it's kind of aimed at them and really trying to, I guess, light a fire for anyone to come across. Just what I'm going to do for a second is just, if I can. Okay, so basically what we're going to talk about, so the BMS wheel. So we've got a number of questions which pertain to BMS. So it's why, what, where, how, when, and who. And each of these questions will have a kind of a subsector which tries to dissect BMS, in each of the different guises. So we start off with the why. For me, the key word's complexity. If you take a traditional home, you probably have a boiler which does heating, does some hot water from a stat on the wall, but not really complex. So the reality of needing or requiring, a fully fledged BMS is warranted. But if you look out of the window there into the wider world of commercial, it's a whole different game. You have ventilation systems, you have hot water systems, heating, chill water. You have zonal conditioning for things like fan coil units and VAVs. You also have air conditioning. So there's a lot of different complex assets that have to work together. So what would be the drivers behind that? Well, comfort. We have to provide a pleasant environment for the end user, the occupants. Productivity. Obviously, to provide a better environment would increase the occupants' output. Energy. We could run everything full tilt, but from an energy perspective, it's not going to be very efficient. We have to be able to integrate with other communication systems, maybe like lighting, fire, access control. And then we have to have regulatory elements like L8, so things like Legionella checking and condition monitoring. It's important that from a BMS standpoint, we can manage all of that. So why specifically do we need a BMS? Well, the BMS really has the power to control 80% of the energy that a building can use. Not everything, but typically. So if you split it down, 52% can be attributed to heat and ventilation and cooling, further 19% to lighting and 9% to hot water. So, from a percentage of everything that can be covered within a building, if you think of your heat and vent, cooling, lighting and hot water, it demonstrates the importance of having as much control under the BMS dictates as possible. Obviously, the lighting is something we don't tend to see, but from a powerful perspective, to be able to manage the energy, it becomes quite important. Okay, so we've just touched on the why. What about the what? What is a BMS? A BMS system is essentially a controller. To start with its fundamentals, it has inputs and it has outputs, and we'll touch on what they are in a second. Within the controller itself, it does a number of functions like data logging, alarms. The application lives within the controller. Obviously, from an energy perspective, you can manage that, and also the control. Then we have the user interfaces. On a BMS system, you typically have two elements. You have a user interface element for engineering. So when the engineer is engineering the controller, they're the ones who have access for things like software engineering and things like that. And then you have an end user interface, which is the visual display. So this is normally the graphic part. So you see, your fancy graphics on the screen. When we start combining multiple controllers, we need networks in order to be able to communicate that data across. And then when we start to get more remote, we need supervisors which effectively manage all of these different elements. If we look at this in a bit more of a simplistic manner, we have a number of layers within the system. So we'll have a controller layer, which will be your controller. And just an important note at this stage that you'll see a lot of manufacturers' systems here. There's no affiliation. It's pretty difficult to try and get the message across without really mentioning certain controllers. So you have this controller layer. You have what we call the field layer, which is physically the inputs and the outputs. So things like sensors and actuators and pumps, differential pressure switches, all of the field devices that are connected to the controller. You then have a network layer, which links the disparate controllers together, and then ultimately a supervisor layer, which is the visionary element. We're going to talk a little bit about the constructs of a panel now, or typically the components of what make up a panel. Panels are normally broken into two sections. The importance of why we do that is really around safety. Gone are the days where you used to find single form panels where you're essentially mixing, power and low voltage or extra low voltage in the same panel. So typically what manufacturers do is we'll provide a 2-form panel or 3-form or even 4, whereby we keep the extra low voltage stuff separated from the higher power stuff. So the low voltage, I think, low voltage is 50 volts up to 1,000 volts, and extra low voltage is anything 50 volts down below. So really, to try and insulate the power is really where we're trying to get that across. So within this panel, we've got, this is just an example of a panel. We've got the BMS section, or the extra low voltage section. We also have power section split up here. If we dive into the control section, so we have the controller, which is normally made up of a main controller and input and output modules, which effectively the field devices get wired to. We have the step down transformer, which is taking the 230 volts, in most cases, down to 24 volts. Then you have your distribution MCBs. We then have a network switch, which when you're dealing with one or more panels, we have this to link the panels together so we can communicate across. And then we have the terminal rail. So typically what happens is we'll build the panels off site, and the panels will be delivered with everything downstream of that terminal rail. So everything's prefabricated, and you deliver the panel on site, you'll install the panel, and then you'll feed the field wires from the disparate field devices directly into the top there. Moving into the power side, so we have our power input, which is where the isolator is. We'll then have our power side 24-volt transformer, which feeds the different things within the power side. We then have the main MCBs that are feeding the various plant items like motors and boilers and things like that. And then we have our control relays, which is effectively the staged switching of the things like contactors, whatever needs to be switched out into the field in a staged format. Just a quick overview of what we've just covered. This is quite a busy slide, so let's just blow that up slightly. So what we're looking at here, this is more of a practical application of how you would probably perceive what we've just looked at in the previous couple of slides. So what you've got here is a basement, a first floor, second floor, and a roof plant. So trying to show you kind of how we would think of piecing this together from a network perspective. So we start with a network Ethernet backbone. So creating basically a little cabinet on each floor with a linked Ethernet backbone. We'll then put in a controller for the basement plant room, covering the wet plant, things like your boilers and your pumps. We'll also include at this stage, the first time we talked about this, is a Modbus interface. The real good thing about Modbus interfaces and just protocols in general is that when you're thinking about Modbus as an example, most most vendors nowadays come with third-party integration capability, and the benefit of that is it allows the end user to not be vendor locked. So it means that if a specific vendor, in this case Trend, or could be anyone, it doesn't mean that you have to just use Trend products. You can use other third-party products. So from a pricing perspective, it allows a lot more choice. So really good that we get this. And in this case, this is Modbus. So we're bringing in a load of meters into a Modbus interface. It allows us to present that Modbus data as just usable values within the screen. On the first floor, we'll put in on the second floor, we'll put in a couple of BACnet interfaces. So again, we're now going into a different protocol. And within the BACnet protocol, we've got a load of BACnet Trend controllers and third-party BACnet devices. Again, similarly to Modbus, it means we have a choice in the type of devices we want to install. And then finally, we'll just wrap this up with a rooftop plant room for ventilation. So although it looks quite complex now, when you kind of break it down and go through it, it's not actually as complex as it sounds. It's just really identifying what each floor requires and how you're going to control it. Okay, so we've touched on the why, we've touched on the what. Let's have a little look at where we're likely to find this. So where do we find BMS systems and how complex can they get? Well, hospitals, airports, offices, these are all places where we find BMS systems. Big venues, that should have been Liverpool's ground there, I did miss a trick. Data centers, big industrial complex sites, and then you can have obviously educational institutions. These are not an exhaustive list. Obviously we find BMS everywhere, but sometimes it's just talking about the complexity gets a bit different. So typically in an office or schools, you have kind of a single LAN, one system with a number of controllers just to do the elements within the requirements. Then you can have more large-scale complexes where you're dealing with multiple LANs. So rather than just having one network, you have multiple networks. Things like data centers, big venues, as I say, things like stadiums and airports. And then you'll have multi-building estates, and this is where you have lots of buildings within an estate. So you go from kind of multi-LAN to remote LANs, communicating across networks. So from a complex perspective, it gets quite meaty as we move forward. Sticking on the where, or moreover where not. So this is in a domestic dwelling, and one of the things we tend to still see in the industry, which can be quite annoying if you're wondering why things are getting hot and cold, is you see things like this where you'll have a sensor or a stat directly above the application. And the problem with that is, of course, when you have heat satisfying a set point on a stat, it just keeps going on and off, in and out, and you don't really know why it's doing that. So sensor positioning is really important for the BMS to operate efficiently. So the message is obviously don't install space sensors in direct streams of the application. That could be anything. It's a radiator here, but it could be a fan, could be air conditioning unit, could be multiple things. This is an example of you're taking this to the next level. So we've got a couple of air conditioning units here providing heating. We've got a sensor on the side there. Next performance, a printer will get put underneath that. The printer itself will emit a lot of heat. And the problem with that, of course, is when you put the heat across a sensor, you tend to find that you'll get a mix of heating and cooling coming from the same unit, which isn't ideal in the sense of you're going to get heating and cooling both happening at the same time. The occupants are not going to be happy. Your energy is certainly not going to be happy because you're working a lot more because you're never going to satisfy the set point. So obviously we'll get a decrease in comfort, we'll get a decrease in productivity for your end users, and you get an increase in energy. That tends to happen a lot. I mean, this probably isn't about the fact that you've got the sensor in the wrong place, although in this case it probably is. It's more around the fact that sometimes other influences can affect the outcome. So it's just being mindful that thinking about where sensors are. One of the big things you tend to see is heaters under desks and things like that tend to affect the outcome of what's happening from things like air conditioning units and fan coil units. So just be mindful of where the sensor is located to not have anything that's going to provide a false positive. To kind of develop this a little bit further, What we've got here is an open plan office, and we've got 3 fan coil units in a what's called a master slave configuration. So we have the master controller on the side there with the main unit with the sensor on the wall. The subsequent units are slaves, which effectively means they follow the same command as the primary or the master unit. So in this sense, in this consideration, we are cooling based on a set point requirement. That's absolutely fine. There's no problem with that at all. All units are doing the same thing. Next thing that happens is they change the dynamics of the room to now have 3 satellite offices or cellular offices. Problem with that is that the sensor's still in that same location. It's in the office. It's not in the other offices, and now we have an issue of a mismatch because we've got the requirements in that first office is it wants heat, and that means that the other 2 offices have to heat as well. So what would we have to do there? Well, quite simply, we'd have to put a master controller on each of them other 2 units and put a sensor in the same 2 offices so that you're effectively all individually controlling each unit. Okay, so we've covered why, what, where. A little bit more about the how now. This is probably one of the more longer sections. So we'll talk a little bit about the field devices. Before I do that though, it's the differences are really analog and digital. We'll touch on analog first, but just as a simplistic note, the differences between analog and digital are quite simple. You've got a digital, which is binary or just on off, a 1 or a 0. And then you've got analog, which is a range of values. So, anything between two different values. So if we touch on the analog, analogs are anything, temperature, humidity, CO2, anything where you've got a number of values that are coming across, in which we can then take data from that sensor. In the case of temperature, it would be something like resistance or could be voltage, and then we'll convert that into a real world value for the BMS system that it can understand. There can be lots of different types. As I say, 0 to 10 volts, you can have current, or you can have resistance for that, and then we'll convert that, as I say, into a meaningful value. We also have digital. These are on-off statuses, so things like presence detection, differential pressure. So if you're reading the pressure value, it's either above pressure or below pressure, so it's only binary. Things like frost conditions, as an example, a frost stat on a heated battery, it's either in frost or it's not above a certain value. So these are kind of the just single point values that you're looking for to be brought back into the controller. You can also have a third one, which is still effectively a digital, but it's just reading it quite quickly, and this is from a digital pulse perspective. So you'll have a scaled value whereby you'll read a pulse, and that pulse can equate to a specific number. So it could be a kilowatt, it could be 10 kilowatts, could be 100 kilowatts, whatever the scaling is. But that will normally be read from the manufacturer, where we're just counting pulses and then putting that value into the controller. If we move to the outputs now, analog outputs. So to be completely honest, it's very same as the inputs. We have analog outputs, and they're normally, not always, but normally they'll range from 0 to 10 volts DC. So in the sense of a valve, as an example, if we're trying to drive an actuator that's driving on a valve, and we want that valve to open up to 80%, that would equate to 8 volts. If we want it to be 50%, it would equate to 5 volts, and so on and so forth. So it directly proportionally scales the voltage to a percentage output. You can offset some of these and stuff, but it's in general, a 0 to 10 volt output will provide a 0 to 100% output. That can also be driven by milliamps as well, and again, scales the same, can be 4 to 20 milliamp. Digital outputs, so just like the inputs, they're just on or off. Simple switching, can be a relay, could be something like a light. Anything that's just a binary status, it's either on or off and doesn't modulate. So taking all that data, inputs and outputs, it's quite an important thing to note, because when it comes to tenders for the likes of companies like ours where we do projects, a lot of the information comes within a tender. A type of information we'd expect to see in a tender is things like schematics, which identify these physical field points somewhere on a drawing. a description, hopefully, about what they're trying to achieve with those field devices, and then a schedule which identifies the type of characteristics within the asset itself that we're controlling. All things being well, it enables us then to create what's called a point count, and this is like for a BMS company, this is kind of the important information to know exactly what you want to do with that system. So in this instance, it's an AHU. Sorry guys, can I just ask someone to mute if they are? There's a bit of feedback coming back. Thank you. So in this instance, it's a handling unit. We've identified a number of analog inputs denoted with the AI, a number of digital inputs denoted with the DI, so on and so forth with analog outputs and digital outputs. And that allows us to create a comprehensive selection then, so we can identify what controllers we need and the inputs and output modules that's going to provide the control for that. Any panel considerations based on the type of voltages we're going to be dealing with, and any user interfaces for that, so as well as network requirements. So that's quite important. You may or may not have heard the term points. It's quite a standard term in the BMS industry. The first thing people will say is, have you got a point count? What point are we dealing with? And that's effectively what a point really is the field device, the end point that's connected to the device. Okay, so that's covered the how. Let's go into the when. So when is obsolete? Obsolete. I do need to caveat this by just saying this isn't to say from a manufacturer's perspective, if a device is obsolete, it renders the system obsolete, because most manufacturers nowadays will provide backward compatibility. This is more a case of identifying if a manufacturer has made a specific device obsolete, that there is more benefits to future products. And I guess as an end user, you have to weigh up the value of the updated version of the said product and make a decision on whether that's important to you as an organization. So we'll touch on trend. There's a number of manufacturers on this, but we will touch on trend. So trend, I've had a number of families. I've had the IQ1s, the IQ2, 3s, IQLs, and they have the 963, which is the graphical interface. We'll start with the IQ1. So as an engineer, if you're going around nowadays and you're looking at systems and you open up panels and you see these kind of things within panels that typically, they're non-supported from a trend perspective. In reality, if one of them devices failed, you'd be hard pressed to be able to find a device to replace it, really. So they're all gone from a trend perspective. IQ2s, these are all the kind of grey controllers you tend to find in panels, and sometimes even in terminal units like fan coil units. You find the likes of IQ2 10s, but again, all obsolete. IQ3, which was the kind of first flagship IP based controller, even now that's now considered obsolete. And then you have things like the IQLs. Now, just as a note of caution on the IQL, the L bit stands for LON. It's a protocol that the IQL communicated across. So we do still find these out in the field. Now, if an IQL had failed in a fan coil unit, as an example, there is no direct replacement from the trend perspective with LON. So you'd have to replace that with a BACnet-based controller. Now, there's no way that we can put on a BACnet controller directly on a LON network. So in some instances, whilst the obsolete comment I made earlier on for backward compatibility is relevant, in some cases it's not. So you are kind of forced in making an upgrade as things start to really fall off. So an IQL, as an example, is LON, and definitely should be thinking about replacing that one. And finally, you have 963, which is the graphical front end for trend. Again, now obsolete. Not just on controls, it's also PCs or operating systems. Considerations to be made. So as of January 2020, Windows Server 2008, Windows 7 is now no longer supported. Windows CE, which a lot of OEM products still use, will be no longer supported from April 21st. What does this mean? Well, from our perspective, all operating models, really, operating systems that are less than Windows 10 are probably not going to be supported. So, you know, if you're thinking about obsolescence and upgrading the control system, we also have to think about the operating system too. Because, you know, if a PC fails and we're still running on a really old system that can't support that system, then you need to upgrade your front end too. Not just sticking with trends, we have Schneider. Schneider have a family of controllers. They have Satchwell, TAC, Andover. We'll start with the TAC. You have TAC Zenter. This was the 401 controller. And you also have a whole host of different types of modules that connect to that controller. Obsolete, I'm afraid. From a Satchwell perspective, we have the BAS 2800. Comes in different types of forms. What you're seeing on the right-hand side of that, there is the power and the comms card, but you had these kind of interchangeable slots that you have inputs and outputs all slotted into a comms card. That's how they look in a panel, big and ugly. Obsolete. And then you have Andover, who have lots of different flavors. You have Infinity, now gone. You have Continuum, also now obsolete. The good thing about Schneider is they did bring in the EcoStructure range, which does make all of these things backward compatible from a front end perspective. I guess the question is, you're still running on the same hardware. So I guess as an end user, you need to make a decision on whether the benefits of not upgrading is something you can deal with. So going back to trends, like this is a slide that perhaps isn't as obvious until the end. So just looking at the dates of when things came out. So the IQ1 came out in 1990 or thereabouts. It was the earliest data sheet I could find for when that came out. 12 years later, we had IQ2s. So 12 years between the two families. 7 years later, we then had the IQ3, which was the first time we come across industry standard IT components. And the benefit with that is because obviously they cost a lot less, they're not bespoke. And it means, you know, anyone can basically create the chipsets from standard industry parts. They also added some backnet capability at this point, which was great. But then just 6 years later, we had IQ4s, or the next family. And I guess the takeaway here is that, you know, the difference from going from manually bespoke IT-based components that you had to have made specifically for the controller to a IT standard industry components, in which case you see the speed in which the families start to become delivered. So the next obvious question is, it's not really the manufacturer that's pushing forward with the new models. It's the speed at which the components are being made and superseded. You're almost forced as an industry now to make new controllers and products, because quite quickly your components become superseded. So it's taking advantage of that, really, especially when things like security and cyber comes into it. It's making sure you're on top of things. So what do I think the future of BMS looks like, more importantly? Where do we think it can go? Well, energy systems, so automatically optimizing the power. So having these smart grids and linking in directly with the grid in order to create things like demand response in a really intelligent way. Reducing power on non-critical items automatically through a BMS system. Location-based services, so locating resources and end users, so identifying things like when you're in meeting rooms, whether there's a whiteboard, just by simple things like RFID tags and understanding where things are, being able to request them through the BMS. Maximizing space utilization, so again, identifying in buildings things like people counting and desk utilization. So, you know, if you're an FD of a specific building, say in Canary Wharf, and you're trying to know whether the floor's being fully utilized, especially if you're paying something like 12 grand a desk a year, you want to know what your utilization rate is. So being able to use that data in with a BMS system, absolutely possible. Agile working, again, using the BMS as a way to book desks, rooms, corporates, meeting rooms, things like that. Harmonizing key FM systems, so utilizing CAFM platforms in order to raise and automate things like fault calls, issues with the BMS to generate a work order ticket directly through a CAFM platform. Automated analytics, using the data collated to start performing reports. Proactive maintenance, so taking all of that data in and starting to look at automated routines, identifying when things like filters are blocked and creating a generated order, rather than kind of, a lot to be said. We have like SFG 20, which will stipulate, you must change the filters on said AHU 4 times a year. The reality of that may not strictly be true. It depends on the location of where the AHU is. Does it need to be visited 4 times a month, or can the data tell us when it needs to be delivered? So that's really where the proactive maintenance element comes in. And then spitting out a nice, easy, digestible report that's user-centric. Obviously, all this provides lower service costs to the end user because you're making it demand-led rather than time-sensitive. Big data, so taking all of this data and recognizing patterns. So not just having data that's collated now with, cloud-based intelligence, but actually data that's being collated over years and making it more about the customer. I mean, a lot of the times we will have a contract where you'll have 4 years on a site, and the end user or the provider of the services will take that data with them. Really what you want to do is collate as much of that data from historic data that's been captured, all to be analysed. Allows you to identify, what to do next. And data-driven monitoring, so using that data to provide information. Seamless user experience, the visitor experience. So again, using things like QR codes that go directly to the visitor. So when they enter the building, they just simply scan your QR code, you authenticate, create a handshake. Things like the lift automatically comes down, it knows where you're going, and then the visitor map then tells you what room you need to go into for your meeting. Future-ready networks. Obviously, at the moment, there's lots of different protocols which are vying for top spots. You have BATnet, LON, KNX, Modbus, MBus. There's lots of these different networks out there, but ultimately, what we need to try to get to, and I think we will do, is one seamless network, but wireless and wired, that'll allow independent communications, almost plug and play, simplistic, with all of your cybersecurity built in. And then, of course, mobile applications. So taking it from the desktop and the laptop and being right in your hand, because that's where the power happens. That's where you, as an engineer, going around and identifying when things are, happening. It's there in the palm of your hands. It means you don't need 2 people on site, things like that. So then taking all of that data together and having a single pane of glass, or a building operating system. So if you think about it, you have things like BMS systems, you have lighting, access control, security, meeting room booking systems, all of these different platforms that are really, really intelligent, but they're not communicating. So having this one common building operating system, so going from a BMS to a BOS, really. Talk a little bit more about wireless communications. So on the left-hand side, we see Enocean, Z-Wave, and Zigbee. Enocean particularly is quite a strong one. Pretty new into the market, but Enocean is batteryless, it's wireless, self-harvesting from an energy perspective, kinetic, solar. So really can run on its own energy. Normally has a little battery that can be backed up. So once you kind of connect it into the gateway, it just provides that information. So things like light switches, leak detection sensors, temperature, humidity, really, really smart stuff. And then you have Zigbee, which is a communication protocol that is self-forming and self-healing. That just means that if you have a number of sensors distributed in a building, and you want to get one, if you've got one gateway that all this information is going through, and one of the sensors fails, it doesn't mean that your whole network will come down. It means that the sensor that's trying to get the information back to a gateway can circumvent it and bounce off other devices. So it's a really good network to deal with Zigbee. We also have Bluetooth. This is really good at the moment. A lot of this, you have things like Blue Water that are trialing things in the retail environment where you've got, I'll just bring up RFID as well, where you have a combination of Bluetooth and RFID, Because the chipsets are so cheap with RFID, they're embedding them in the tags on clothes. So it means if you're a customer and you're going into one of the shops, it means you can, well, once you've authenticated on the Wi-Fi, it starts sending you automated ads directing you to specific things like sales elements. So another example of that is where you've got like automated cameras that are identifying things like population density. So when you go into a store, they know where the amount of people are kind of gravitating towards. So that from a retail perspective, you know where to start putting your advertisement campaigns because that's going to get most traction. So things like RFID and Bluetooth combined are starting to be really powerful within the retail world. And then we have what we'd probably suggest is leading the pack with LoRaWAN. LoRaWAN can travel something like distance of 10 kilometers. So having one gateway in a building and allowing a sensor, to communicate over 10 kilometers is quite powerful. You can have up to something like 1,000 devices all going into one gateway. It really means, from a data perspective and trying to get this data back into a gateway, a lot of the issues fall with wireless communications. Wireless in the past has always been known as a risk because of the communication issues, different bandwidths in which it's communicating on. So LoRaWAN, we think, is quite a powerful one which addresses a lot of those issues. Okay, finally we land on the who. So who are the players? So within the BMS industry, there's dare I say, it's much of a muchness. They all offer compelling systems. They all have similar types of controllers, similar types of modules that can do similar things. You have Sauter, you have Trend, Honeywell, Structureware, which is obviously Schneider. You have Tritium. Tritium is probably a really powerful one in relation to lots of open communications. But they're all there. I mean, this again isn't an exhaustive list. There's lots of different manufacturers out there, but I guess within the BMS world, these are the types of manufacturers we come across more often than not. So just to finish off, this was an introduction to BMS. It's aimed at people who are trying to get into the industry, have a feel for the industry, wanting to know a bit more about it. If there are any questions, I think there's maybe some questions in the chat, which is fine. But post this. If you are watching the recording of this or you haven't had a chance to ask a question, by all means, just drop me a message. I'd be more than happy to communicate. And thank you very much, really.